Have you ever been in a room when the power surges? The ceiling fan starts spinning wildly, and the lights begin flickering violently. It's a terrifying moment because you know exactly what might happen next. Hidden away inside your appliances, tiny, delicate components are receiving far too much energy, heating up and bursting into flames. To understand why this happens, we have to look at how electricity behaves. By its very nature, an electric current flows from an area of high electrical pressure to an area of lower pressure, and electrons are inherently greedy. If you give them a clear, unobstructed path between a negative and a positive terminal, they will rush through that path as fast as physically possible. When millions of electrons stampede through a metallic wire without anything to slow them down, they generate an enormous amount of friction. That friction rapidly builds up as intense heat. Left to run wild, electricity is entirely destructed. Without built-in brakes to control the flow, metal wires melt, the components shatter, and the entire system fails. Look at this diagram. A 9-volt battery is connected to a fragile green LED, with electrons racing dangerously fast toward it. To protect the LED, we add a resistor. The moment we place it into the path, the rushing electrons are forced to slow down. This relationship is defined by Ohm's law. Increasing the physical resistance forces the current to drop. Looking back at our circuit, the battery pushes with 9 volts, but our LED can only survive 2. That leaves a dangerous discrepancy of 7 volts. The resistor takes up the excess voltage. By carefully calculating the resistance we need, we can size this component to absorb exactly those 7 excess volts, leaving the LED completely unharmed. Resistors are the dedicated traffic controllers of your electronics. They purposefully sacrifice their own energy to protect the fragile components further down the line. But how does a simple cylinder actually absorb all that excess energy? Inside a standard ceramic resistor, there is a tightly coiled metallic wire core. The resistor captures that rushing energy, converting the movement of the electrons directly into physical heat. Because of this, every resistor has what is called a power rating. This rating dictates the absolute maximum amount of heat the component can dissipate into the air before destroying itself. If you ignore that rating and force massive voltage through a tiny half-watt resistor, it can't shed the heat fast enough. The safety device itself becomes a fire hazard, blistering and burning up. By calculating the correct power rating for the job, you ensure the resistor only gets slightly warm, safely radiating the heat away without failing. Keeping a circuit safe isn't solely about doing the math to limit the current. You also have to ensure your components are physically large enough to survive the heat they are designed to generate. Once you know how to limit electricity, a new problem emerges. What if you want to change how much current is flowing while the device is running, without having to melt metal connections and swap out permanently attached parts? That's where the potentiometer comes in. A potentiometer is simply a variable resistor. It is a device where you can easily adjust the total resistance of a circuit. Inside this animated diagram is a curved resistive track. Turning the dial changes the distance electrons travel, adjusting resistance. At maximum, it chokes the current, causing the LED to fade. Turning it back removes resistance, opening the valve so the LED shines brightly. Remember the terrifying sparks and flames that happen when an overloaded circuit fails? When we properly utilize these deliberate limits, that chaos is entirely prevented. The staggering, explosive power of electricity is only useful to us because simple components like resistors provide the physical brakes we need to tame it.